So in the last class, we conclude the analysis of the Gilbert's multiplier cell. But for it to be useful, it needs some associated circuitry. Now the circuit which you can see before you is now a practical Gilbert's multiplier. The only part which is missing is the output part. I could not draw it over here because if I'm to draw it over here, it will take a lot of space. This is what I mean. Let's just see if I can get you a complete. Semi does not want us to see. Okay, this is the on-semi multiplier, the MC1495. It was a linear 4-quadrant multiplier with some information here, excellent linearity, because it gives you a lot of technical information. And this is the schematic of what is inside. So you can see on the left-hand side, you got the left-hand side here, we've got this circuit, which is known as a pre-distortion circuit. And if you look at Q5, Q6, Q7, Q8, and this Q3 and Q4, these are our equivalent of Q5 and Q6 in our other one. So in this IC, the one is showing you two parts of it. The input part, which is the pre-distortion circuit, and the Gilbert's multiplier cell. And to get the output with respect to the ground, you use here, you use this, in this case here, you're using some two other ICs, which are just differential amplifiers with respect to the ground. Let me see, the other one was also on semi. But they put a lot of watermarking. The same company. This is MC1494. The other one I think was MC1495. It's almost identical inside, but you can see the outputs use another differential amplifier. The output would make the output with respect to the ground. Let me see. Okay, this is actually the complete circuit. A bit complicated. As you can see, the MC1494 is what is inside this dashed, the dashed area. Where your Gilbert's multiplier cell, you can see it over here. Where is it? You can see the Gilbert cell is this one. And then the output goes here. The output, you can see, the output goes to this part of the circuit over there. And then you get a current output at the top over here. So that will be designed to make the output with respect to the ground. So let's just go back to our, notes. So what I wanted to say is that this is a practical multiplier. The only part which is missing is the output side. And I've shown you how to make the output with respect to the ground. So a practical multiplier has got three parts. It's got the input part, which we are calling the pre-distortion circuit, or the preconditioning circuit, whose function is to extend the linear range of the input V1. Normally our input V1 was here. That was our first voltage, or your input Vx, and this was your second voltage, V2. It's connected over here. And then since the output is floating, you need to connect a differential amplifier. So this is R, AR, so that you get an output with respect to the ground. So this is your point A, this is your point B. So A will be here, and maybe B will be here. That's the output. So that will be a complete multiplier circuit. So the output with respect to the grounds, the two input signals also with respect to the grounds, and the dynamic range of the two input signals are the same. The resistance seen by the two inputs in this diagram over here, it's Vz, and I think Vy. This diagram which is being displayed sees the two inputs the same, the dynamic range is the same, and then we get the correct answer. Now, if you look at, I'll still only concentrate on the Gilbert's multiplier cell and its associated circuitry for the time being. The preconditioning circuit, which comprises of Q7, Q8, and the constant current source Q13, and I think Q14 there. We're going to leave it for the time being. I'm only going to still concentrate on the Gilbert's multiplier cell because that you can see the different ways of generating the constant current source. So today, that's what I wanted us to analyze. So I want us to still concentrate on the Gilbert's multiplier cell, and then this type of connection whereby you got R1 at the emitter of Q9, you got R1 at the emitter of Q10, then you got another resistance in between them, bridging them, and that's when you got the constant current source of Q10. Is it Q15? Q15, this is Q15 and Q16. Remember, in the earlier arrangement, it was slightly different. We had an RE. I don't have it here. I don't think I have it here because let me just see. Oh, we had an RE. We had Q5, Q6 was in this form. This was our Q5. And this was our Q6. And the current is I5. Current here is I6. And we remember we analyzed the circuit where the emitter of Q5 was equal to 0 and emitter of Q6 equal to 0. Height affected the performance of the Gilbert multiplier. And then we introduced RE and we analyzed its performance when RE is included. Height affects the output. Okay, and we found out that the gain decreases. In fact, equation 27 here, equation 27, or rather 26, was the equation of the output when R is equal to 0. We get V naught is minus V1 RL IT V squared over T squared. But with RE, so this was case 2, RE not equal to 0, we got the output as equation 34. V naught is minus V1 V2 RL divided by VT RE. So if you compare 34 with 26, you'll find that the effect of RE is actually decreased. The effect of RE in 34 is decrease the gain of the system. But improve the dynamic range of the signal V2. If RE is equal to 0, then the maximum voltage of V2 is obtained from that of just as a normal differential amplifier, which is approximately 4 VT. From the analysis of a differential amplifier, this is V2, and this is here I5 and I6. Then if you had to solve the equation, if you call this IEE, and this is just our normal differential amplifier. And if you plot I5 and I6, you get a curve like this. The sum of the two is always equal to IEE. And the point where I5 approaches 0 and I6 approaches 0, or I5 approaches 0, I6 approaches maximum, is approximately 4 VT. And since VT is 26 milliamps at room temperature, 26 millivolts, this is approximately 100 millivolts. So this axis is here V2, or it could be V1. So that's not very useful alone, because we want a light dynamic range. We want to multiply maybe signals which are maybe 10 volts times 10 volts, or plus minus 10 volts times plus minus 10 volts. Okay, so by including RE, we can extend this range a bit, as we shall see. So that's what we concluded in the last class. So these are the summaries of the last class. Limitations. Number 1, the range of signal V1 is less than plus minus 4 VT, approximately 100 millivolts. And the dynamic range of the signal V2 will be approximately IT into RE. That is if RE is present. If RE is not present, then the dynamic range of the second signal is also just plus minus 4 VT, which is 100 millivolts. Then the two signals do not have a common ground. And then thirdly, we saw that the two signals do not see the same resistance, and therefore the need to create a practical Gilbert's multiplier, which is our topic today. So let's consider our Gilbert's multiplier cell with this arrangement. So in this new arrangement, we got resistance R1 at the emitters of, in this circuit, it's Q9 and Q10. In our old system, Q9 and Q10 was actually Q5 and Q6. All right. So in our old system, you can use the if you're only considering the Gilbert's multiplier cell, we can still call them Q9, we can call it Q5, and this is Q6. We'll forget about the preconditioning circuit for the time being. So let's show that this arrangement can also result in the circuit multiplying. As I said, most companies do not like you to copy them, so otherwise they sue you. So if you came up with a circuit where you have your REs, as we analyzed the first one, and built your IC chip, the companies can sue you. Just the way Samsung was being sued by Apple for making their phones similar to Apple. Okay, so let's analyze this type of configuration where we have R1 here, R1 here, and then a bridging resistor of 35K, and this transistor Q, this one is Q15, this transistor is Q15, and this is Q16. This actually forms the constant current source. This forms the constant current source. Okay, so normally when I ask students to get the DC bias of the circuit in the exam or the CAT, they do not know how to approach it. Now, in this circuit over here, you can see this IBB is a constant current source. IBB is a constant current source over here. So, if the gain of the transistor is high, then we want to determine IT by 2. We call this currents over here IT by 2, IT by 2. So what will be the current in the emitter of Q17? What will the current be? So the current will just be IB by 2. So this current over here will just be IB. Should just be IBB. And the voltage at the base of Q17, I think it's VP, is not very clear. This voltage here, VP, will be equal to what? It will be equal to 4K times IBB plus VBE of Q17. Let's do it neatly. So VP, I'll just write it here. The voltage at the base of Q17 will be equal to the drop across the 4K at the emitter, and the drop is IBB times 4K plus VBE 17. And therefore, we can get the current at the emitter of Q16. This is Q16 here. And this one is Q15. So if the base of Q17 is identical to the base of Q15, which is identical to the base voltage of Q15, which is identical to the base of all these other transistors, Q13 and Q14. But we'll only restrict ourselves to analyzing the currents at the emitters of Q15 and Q16. So let's consider the current at the emitter of Q16. So if the base of Q16 is VP, the emitter will be VP minus 0.6 volts, or minus VBE 16. So we can say that IE of 16 quiescent will be VP minus VBE 15 all divided by 8K. And this will be equal to our top equation here. Let's call this one equation 1. So equation 1 gives us VP. So VP minus VBB of 15 in the numerator will just remain with IBB into 4K over 8K. And this is just 1/2 of IBB. So in this circuit, if you got IBB from a constant current source, the currents here, I just put it next there, the currents passing here, and the currents passing here, and even the currents passing here, the currents passing here, all of them will just be 1/2 IBB. So if IBB is 1 milliamp constant current source, then these currents at the emitters of the transistor Q15 and 16 will just be 1/2 of it. All right, now in our analysis, these currents at the emitters, I'll be calling them IT divided by 2. IT is a total divided by 2. Because now we've got two current sources. In our earlier design, Q5, Q6, we're just calling this current I total. We're just calling this current IT. But now we have two current sources. So I'll give them a name, IT divided by 2. Okay, so let's start the analysis. Now that you've gotten some basic idea of what's happening. So we got a normal Gilbert multiplier cell, but then we got a modification.
Excuse me, sir.
Yes.
I wish to seek a clarification concerning the calculation for IE16. Would the negative voltage, the minus VEE, affect that calculation, or do we just use the emitter voltage alone?
No, the negative does not come into play. It doesn't come into play. But if you want to use it, you can use it. It doesn't matter. You can start from minus VEE plus VBEQ17, right? But since I'm using them as I'm using minus VEE as a common reference, okay? Just as a common reference, I know it's negative. So the drop from minus VEE to the emitter of Q17 would be IBB times 4K. All right. And then the base voltage, which I'm calling VP, would be the drop across the 4K resistance at the emitter of Q17 plus VBE. And this voltage is VP. So the same voltage VP appears at the base of Q16. So to go to the emitter voltage of Q16, I have to drop VP minus VBE of Q16. Now the VB is identical because this is fabricated in one chip. Okay, this is an IC chip. So this is fabricated in the same silicon wafer. So the VBs will be identical. Okay. So it won't affect. You can analyze it from minus VBE plus 4K into IBB plus VBQ17 should equal to VP. And then to get the emitter current of Q16, you take that whole equation minus VEE plus the drop across 4K plus VBQ17 minus VBQ16 will give you the potential at the emitter. And you'll still find that the current is still obtained by the potential at the emitter, which is VP minus VBQ16, all divided by 8K to find this current. Is that okay?
Yes, it is.
Let's continue. Wow. Okay, so we want to see how the collector currents of Q9, Q10 varies as a function of V2 for this new configuration, where we got R1 and we got this 35K. Now to make life easy for us, I'll consider it in two cases. Case one, when R1 is equal to 0, and then in case 2, I'll include the effect of R1, and we'll see how our I5 and I6 changes. Remember, our I5 for the nomenclature we're using for our old circuit. So I5 is not but the collector current of Q9 over here, and I6 is the collector current of Q10. Okay, so let's start. So I've called it analysis of new scheme. I can write of the new scheme. Analysis of the new scheme. Differential voltage to current converter. We are calling it a differential voltage to current converter because the currents are the currents in the collectors of Q5 and Q6. And the voltage is the voltage V2. So this is case one, where you can see I've removed the emitter resistance R1. I'll remove the emitter resistance R1 here. There's no R1 over here. Okay, there's only that 35K, which is RE. I'm calling it RE over here. And then the two constant current sources, I'm calling this first current source IT by 2, IT by 2. Okay, means each of them provides half the total constant currents at the emitters of the differential amplifier. That's why I'm calling it I total divided by 2. The T there stands for total. Okay. So I've just used my old nomenclature. The transistor, bottom left is Q5, bottom right is Q6. So let's analyze this circuit. We want to find the relationship between I5, I6, and V2. Or in other words, how V2 varies the currents I5 and I6 in this new configuration. So for this, I've said let's apply KVL to the loop. A, B, C, D. Now in my diagram it's not there, but I can write it for you here. This is what I mean. A is the base of the first one. D is this point. C is this point. D is this point. And remember our currents, we'll call this one I5. And we'll call this one I6. So the emitter currents also will be, here will be I5. And this is I6. Now that I'm using capitals, once again, for this case now, these are dynamic currents. These are signal currents. These are not biasing currents. Okay, so let's apply KVL to the loop. So I start at the base of Q5 over here. So I can write V2. I drop VB5 minus, and I'll be calling this current, this unknown current here, I'll be calling it IX since it's unknown. That current, I'll be calling it IX. Okay, so let's start at the base of Q5. So the potential at the base of Q5 is V2. Then I drop minus VB5. Then I drop again VRE. VRE is the voltage across this resistance in between the 2 points, C, B, and C, plus VBE6 should equal to 0. So this is the definition of VRE. So I can make V2 the subject. I make V2 the subject, I'll get V2 is VB5 minus VB6 plus VRE. And then from Eber-Mold relations, IC is I0 e to the VB, or the way we needed VT minus 1. We can get what is VB5 and VB6 using the approximations we studied earlier. So VB5 will just be VT natural log I5 divided by I0. Or you can write I0 5, but these are matched transistors. And similarly, VB6 is VT natural log of I6 divided by I0 for VB6. So if I substitute results 3 and 4 in 2, I'll get a V2 can be written as a VT natural log I5 divided by I0 minus VT natural log I6 by I0 plus VRE. So we can leave it there like that for the time being. We'll come back to it We'll simplify it further. But now let's consider what's happening at the nodes. So for this, in your diagram, if it's not very clear, if you're using a small screen laptop, this node over here, I'm calling it E. This node, and this other node over here, I'm calling it F. It's printed, but it's not very clear in the circuit. It's not very clear in the circuit. So if you look at node E, the current going into the junction E is I5, should be equal to current going away from the junction, which is IT by 2 plus IX. And if you look at node F, current going to the junction is I6 plus IX. Current going away from the junction is IT divided by 2. So you can form equations in terms of I5 and I6 at each of the junctions. So for the node junction E, for the junction E, it's very easy. I5 is just equal to IT by 2 plus IX. And for this junction over here, this other junction here, junction F, we've got I6 plus IX is equal to IT by 2. So we can write that I6 at that junction is equal to IT by 2 minus IX. So that is what I'll put in the equations. So this is at F, and at E, we'll have this equation. It's just simply I5 is equal to IT by 2 plus IX. So those are the results I'm going to be using over here. So this is what I've done over here. So applying KCL at node E, I5 is just IT divided by 2 plus X. That's what we did over here. I5 is just IT divided by 2 plus IX. And similarly for the next one, KCL at node F over here is I6 is IT divided by 2 minus X. So equation 6 is I5. Equation 8 is I6. Now let's solve for the unknown current IX. Now to get IX, we solve the two simultaneous equations, I6 and the I8. And a simple way is just subtract I5 minus I6. You'll get IX from those two equations. So from this one and from this one. So I5 minus I6 will be equal to the first one, which is IT divided by 2 from 6 plus IX, that's I5, minus I6 from 8 is IT divided by 2 minus IX. So this is your I6 and this is your I5. So if you open the bracket, you'll get IT divided by 2 plus IX minus IT divided by 2 plus IX. And this will give you just 2 IX, because this IT will cancel with this IT. So that's how we get equation 9. This is how I get equation 9. So there's a typing error here. It is corrected. So this is 2ix. And therefore, we can solve for ix. Ix will just be I5 minus I6 divided by 2 will be Ix. That's how we get 10. And therefore, we can get the voltage drop across Re, the voltage drop across Re. And this is this resistor here. The voltage drop across this resistor here is just Ix into Re. So that is what I've written over here. So VRE is the voltage drop across Re is just Ix into Re, which is just I5 minus I6 divided by 2, which is the value of Ix into Re. Now let's sub all these results in equation 5. This is equation 5 over here. So we've known what VRE is. Now let's simplify these natural log terms. So the first term is Vt natural log I5 divided by I0. Second term is minus Vt natural log I6 divided by I0. So now we can simplify the whole of this, get the common terms. So the common term will be Vt natural log I5 just divided by I6 plus VRE. So that's how we get this equation here. The I0 will cancel. So they cancel because Q5 and Q6 are matched. So the I0s cancel one another. Now let's substitute for values of I5 and I6. Remember, I5 was equal to IT by 2 plus Ix, and I6 in our circuit was equal to IT divided by 2 minus Ix. So that's how we get 13. And if we multiply the bracket of the natural log numerator denominator by 2, we'll get natural log of IT plus 2Ix all divided by IT minus 2Ix plus Re into I5 minus I6 divided by 2. So this term remains the same. Next, I've said that for a small delta I, which is 2Ix, implies natural log of 1 is equal to 0. So what I'm saying over here, if 2Ix is small, then the numerator of the natural log is approximately equal to the numerator of the denominator of the natural log, and natural log of approximately 1 is 0. So equation 14 just remains with the right-hand side. And that's what I mean over here. So we can say that V2 is approximately equal to, you have written equal to, but it's actually approximately equal to Re over 2 into I5 minus I6. Now this equation 15 tells us how I5 and I6 are affected by the signal V2. So they obey this equation over here. So this is how I5 and I6 are related to V2, equation 15. Therefore, we can now substitute this result 15 in our original equation, which I've just put it over here. In our original equation of the Gilbert's multiplier that gave us V0 as a function of V naught as a function of I5 and I6, which is 16 over here. I've already given you that original equation. It's 16 over here. So in the original equation of our Gilbert multiplier, V naught was equal to minus RL V1 by VT I5 minus I6. But we know for this new configuration, the relationship between I5 and I6 is given by 15. So from 16, I can substitute the value of I5 and I6. So from 15, you can say 15 implies I5 minus I6 can be written as 2V2 over RE. So that is what I've done to get 17. So this term over here which is this one, is just obtained from this substitution here from 15. So now we get the output as a function of both V1 and V2 for this new configuration. So for this new configuration, V naught is minus RL V1 into 2V2 all divided by VT into RE. Or put in a better form, we can write V naught is minus, take the 2 first in equation 17, 2 RL V1 V2 over VT RE. Or you can rearrange it further, divide numerator by 2 and divide the RE by 2. So you get V naught is minus RL V1 V2 over VT RE divided by 2. And this is actually equal to the standard form where V naught is equal to some scalar K V1 V2. So you can see the multiplication is still there. The only difference with this circuit and the first one is that the gain for the first, remember the first earlier circuit we did? Let's look at it here. The old technique, the very old one. Yeah, this one had an array. This one, this circuit where this is Q5 and Q6 with the array in this form. So with that design, V naught was minus V1 V2 RL over VT RE. But with the new design, with R1 is equal to 0, if it use the same REs, then this one now the gain will be more because in the denominator we got RE divided by 2. So I've given a simple exercise here. Compare the two configurations of the linear differential voltage to current converters and give two circuits with equivalent gain. So it's just application of equation 19 and the other equation. So if you want them to have the same gain, then for this design, the second design, which we've done just now, the RE must be twice the first one. So just a simple exercise. Now let's go to part 2, or case number 2, where we analyze the circuit, but now taking into account the effect of R1. in the differential voltage to current converter. So this is now our circuit now. So once again, you can consider this to be our Q5. This is our Q6. So this will be your I5. And this will be your I6. And it means the emitter currents. This will be I5. And this will be I6. And once again, I think, I don't know, in my notes, maybe you can consider this node E. I don't know. I'll check in the notes what I've used. So this node over here, we use this. So now it's applying KVL at point A, meter B, this point C, D, E, F. The current sources are still IT by 2 and IT by 2. So we want to see how the circuit is affected by including the emitter resistance R1 in the circuit. So we want how current I5 and I6 relate to the signal V2, where now we have R1 in the circuit. So we just repeat the same procedure as we did first. So we apply KVL to loop A, B, C, D, E, F. So if I start at A, I'll get V2 minus VBQ5 minus the drop across R1 minus the drop across RE. So once again, the current, unknown current passing through here, I'll be calling it IX. So let's apply KVL to loop A, B, C, D, E, F. So I'll get equation starting from A minus VB5 minus I5 into R1 minus IX into RE plus I6 into R1 plus VB6 should equal to 0 because the bottom part of V2 is 0. So that's how I get my equation 1. So let's make V2 the subject. So the terms which were negative on the left-hand side become positive. So like this minus I5 into R1 becomes positive, and the positive turns I6 into R1 becomes negative, and VB6 becomes negative, VB5 becomes positive. So I'll get equation 2, which gives us V2 is VB5 minus VB6 plus I5 minus I6 into R1 plus VRE. And then from Ebermol's relations, we can get VB5 is just, if neta is 1, it's just VT natural log I5 by I0, and VB6 is VT natural log I6 by I0. That is for March Q5, Q6, March Q5 and Q6, and neta is equal to 1. So for that, we can write equation 3. So let's substitute these results in equation 2. So you get V2 is equal to VT natural log I5 divided by I6. When you combine the VB5 minus VB6, plus I5 minus RE into R1, this term over here, and plus the voltage drop across the resistance RE4. So next, let's apply Kirchhoff's current law at node E. So at node E, this is your node E, this is your RE, this is your current IT by 2. Onyango John, switch off your mic. So that's the situation we have. I'll just do it there so that I don't flip the pages left, right all the time. So this is your Q5 and Q6 over here. So KCL at node E is here. We can write that I5, that's current going towards the junction, is equal to current away from the junction, which is IT by 2 plus IX. And similarly, applying KCL at node F over here, we can write that current going towards the junction is I6 plus IX, and current going away is IT by 2. So we can write that I6 is IT by 2 minus IX. And then I can solve for IX the way we did earlier. Here I've taken a shortcut, of course. What you do is, so how I got this is just like how I did. Okay, use I5 minus I6. You'll get it as 2IX. We've done it earlier on. That's why I just put the answer there. And therefore, IX is I5 minus I6 divided by 2. So in equation 4, we're able to get the voltage across the resistance RE, which is IX into RE. So all that remains is for us to simplify. And the remaining part, FET into natural log I5 divided by I6. So I've said yes, sub equation 8 in 4, you get 9. So in equation 9, all I've done is just substitute for IX is equal to I5 minus I6 divided by 2 into RE. That's all I've done from 4. Next, I combine these first two terms with natural log. Natural log I5 by I6, but I know what I5 is. I5 is IT by 2 plus IX. I6 is IT by 2 minus IX. The rest remains the same. Right-hand side of 10 remains the same. So we try and simplify what's inside the natural log bracket. So you multiply numerator, denominator, the natural log of 10 to get 11. So now you get natural log IT plus 2IX, all divided by IT minus 2IX. The rest remains the same. Then I use a substitution, a delta I I've substituted delta I is actually a 2ix and said that for small delta I implies natural log of 1, which is 0. So 12 can be simplified as just equal to V2 is approximately equal to, although I've used the term equal to, is approximately equal to, let me see if I can, that's slightly better. So V2 is approximately equal to I5 minus I6 into R1 plus RE divided by 2. So now we've gotten equation 13 tells us the relationship between I5, I6, and V2, and how it's affected by R1. So once again, equation 14 was our original output as a function of V1 and I5 and I6, or our earlier differential amplifier, but now I5 and I6 are related to V2 as per equation 13. So from equation 13, we can write I5 minus I6 is just equal to V2 divided by R1 plus RE over 2. So if I substitute this result, I'll get equation 15. For those who might not follow, what I'm doing over here, this implies that I5 in this new design minus I6 is equal to V2 over R1 plus RE divided by 2. So I've just substituted this result over here for this in 14. And if you do that, you get equation 15. So for this new design, V0 is minus RL V1 V2 all divided by VT into R1 plus RE divided by 2. Or we can write it, if I substitute Rx double dash to be equal to RE plus, sorry, R1 plus RE divided by 2, then we can write the equation as V0 is minus RL V1 V2 over VT Rx dash. And you can see that this is still the same as equal to our standard form, which is our K1 V1 V2, well, the scalar K will just be RL divided by VT into R1 plus R2. So if you look at equation 15 here and compare it, so equation 15, you can see there's R1 in the denominator. So the effect of R1 is actually decrease the gain. It actually decreases the gain of our multiplier. For example, if R1 is equal to 0, then in the bottom bracket, all that remains is RE by 2. But if R1 is something, then you go to add R1 plus that RE by 2. So I've concluded and said that the effect of R1 is to increase the local feedback, thereby improving the linearity of the voltage to current conversion. This results in a gain reduction at the output of the multiplier. I should have written as given by 15, as opposed to when R1 was not there, where the output voltage V0 was equal to minus RL V1 V2 over VT, or divided by RE divided by 2. Now R1 also increases the linear dynamic range of the signal V2. Now that can be shown from this equation that V2 is natural log into brackets. All this time we had done it before. This is just obtained from this equation 12 over here, which is related to 11 like this. So from this equation, which I'm calling A over here, if delta is small, then this equation can be approximated, because natural log will be approximate natural log of 1, which is 0. So the voltage V2 will be approximately I5 minus I6 into R1 plus RE divided by 2. Now I don't want to go into all this again. We've already done it. Now from that circuit, from the practical circuit, okay. Okay, let me just prove to you what I'm trying to do over here. I want to prove to you that it increases the dynamic range. It decreases the dynamic range. Now equation V2, equation B, which is just equation A with the first natural log time equal to 0, we can write that V2 as I5 minus I6 into R1 plus R2, which is just the right-hand side of A. And then if you do from the analysis at node E and F, we've done all this. Let me just try to get this one. Look at equation B over here. V2 is I5 minus I6 into R1 plus RE divided by 2. But I5 is this, I6 is this, and I5 plus I6 is always equal to IT. So we can consider the case when I5 is equal to 0. So the first term here is 0. And therefore V2 will be 0 minus I6 into brackets R1 plus RE divided by 2. But when I5 is equal to 0 from this equation over here, I6 is equal to IT. So V2 will be minus IT into brackets R1 plus RE divided by 2. And similarly, when I6 is 0, so it means the currents are transferring from one transistor to the other. So when I6 is 0, use equation B over here. When I6 is 0, V2 is I5 into R1 plus RE divided by 2. But we know that I5 plus I6 is always equal to IT. So I6 is 0. So it means this term here is 0. So it means I5 is equal to IT. So if you substitute that second case, this second case over here, when I6 is 0, then V2 will be just be IT into R1 plus RE divided by 2. So we consider two extreme cases. One, I5 is equal to 0. One, IT is equal to 0. So while I'm considering that, remember from the differential amplifier, the currents tend to be like that. So let's assume this is your I5 and this is your I6. They interchange. So I've considered the two extreme ends. So I5 is equal to 0 is somewhere here. I6 is equal to 0 is somewhere here. So this is the voltage. This is the differential voltage. Okay, so the dynamic range is this range over here. The range of input, actually this is your V2. Is the range of voltages. And that range of voltage of V2 will now be given by V2 is plus minus IT into R1 plus RE divided by 2. So this will be for the positive end, this for the negative end. So this is the maximum magnitude of the signal V2, which is much, much greater than that if there's no emitter degeneration resistance. Okay, for the case whereby the resistance at the emitter is 0 for the differential amplifier, if you draw those curves, you'll find that we found that from here to here is 4 VT, which is approximately 100 millivolts. But now in this case, V2 can take a value approximately plus minus IT into R1 plus RE divided by 2. So you're told, for example, for the circuit above, I want us to do this for the circuit above. What is the circuit above? That is our practical circuit. If you're told to find out what is the dynamic range of the signal V2, given that IT is 0.3 milliamps, and therefore IT by 2 is half of that, which is 0.015 milliamps. So this is the problem for our practical circuit. So this is the problem. So ABB is 0.3 milliamps. So each of these IT by 2 is 0.15 milliamps. So here you get 0.15 milliamps, each of these. So you're told to find out what is the dynamic range of signal V2. What is the maximum range that signal V2 can have? So from that analysis, we found that V2 can take values plus, minus, IT. I think it was plus minus IT. Let me just confirm. V2, equation E, plus minus IT into R1 plus RE over 2. So I've done the problem over here. R1 is 25K. RE is 35K. So RE by 2, take this, sorry. So if you use this equation over here, you get V2 equal to IT plus minus IT. IT is 0.3 milliamps into R1. R1 is 25K plus 35K divided by 2, that is 17.5. So if you add 17.5 plus 25, you get 42.5. You get 45K. And no, it's not 45, sorry. 17.5 plus 25. It's 42.5. So 42.5 times 0.3 is 12.75. Which is a very good dynamic range, because the maximum supply voltage for these ICs are typically maybe 15 volts maximum. So I think I'll stop there for now, and we go to the labs that Moses sent me. So I hope there's no problem here. All we've done from our earlier multiplier is not to consider a practical multiplier. And now we've finished everything to do the Gilbert multiplier cell and this new technique of biasing Q 9 and 10 in this circuit. So all that will remain is for us to analyze the pre-distortion circuit. We've proved that this circuit will multiply when R1 is 0. This circuit will multiply when R1 is something. The effect of R1 is just to increase the linearity at the expense of the gain of the system. So in the next class, we shall do this preconditioning circuit. We shall do this preconditioning circuit. So any questions on this? Any questions on this so far before we move to the lab that Moses sent to me? Any questions on this? When asked the biasing of this, no student gets it right. No student gets it right. And I think in your third year electronics, you should have studied current mirrors. Any questions? Are you guys there, or are you left? Who has left? Switch on your mic. Okay, now let's go. Okay, so let's go to the lab that Moses sent me. Moses, why is your photocopier black? Or your scanner, it's black. So in the lab, derive an expression for the output we've done. How many quadrants we've done? Determine the appropriate values of resistors, capacitance, and the first supply. C, connect the circuit and vary V1 and V2 and measure the corresponding outputs and output voltages. Plot V0 versus inputs V1 and V2. How will you plot? Unless it's a DC, unless you put DC voltages. Unless the DC voltage you can't plot. So something capacitors, so you can't pass DC to the capacitor. And you're told note that one of the inputs should be kept constant and the other varied. What have you people been doing? Unless maybe in this bottom one here, you connect it to DC to vary the transconductance. Now, Moses, what are all the scribbles you people have drawn over here?
And the manual is provided when it's that way, so it's a very previous scribbles. Maybe they were trying to derive some output equations.
I think just generally you have to prove that this circuit can multiply, right? For this other part, this part D, connect the circuit, vary the input voltage V1 and V2, and measure the corresponding output voltage V0. Plot V0 versus the input voltages V1 and V2. This part of the equation can only be done if there are no capacitors. And you're told to note one of the input voltages or one of the input voltage needs to be kept constant while the other is varied. Then part E, carry out the analysis of the results obtained and compare with the theoretical parameters. The second last part can only be done if for the second signal put over here is a DC without a capacitor. Otherwise, once you put a capacitor here and you got another capacitor at the input of the first one, you're going to have actually a four quadrant multiplier. So I think the problem here is just the design. The problem here, you got two problems here. One of them is the design and the other is how to use the oscilloscope. And that was the biggest problem. Okay, let's see. So your circuit looks something like this. What happened again? I think. So once you put a capacitor at the input, then it means you can only supply AC. Now this second signal, this is what brings the problem. Because the second signal you applied So you're told to design for the capacitors, Moses? Moses, are you told to design for the capacitors or you're already given capacitors?
We designed for actually most of the groups were coming with their own circuit. We were not exactly using this one. You could use this one or opt to simulate your own. Okay, from of course a multiplier circuit diagram and come implement in the lab.
This should not be for fifth year. This is supposed to be for third year. Or fifth year, you should do the Gilbert multiplier. Okay, let's do it. So essentially, this is the circuit. This is the circuit. So this resistances, this will be your RLs. And this is your biasing resistors, which normally call RB. Now for small signal transistors, what transistors were you given? Were they the BC series? Moses or
Yes,
anybody else? Eh?
we are using BC508.
BC508.
548.
508, not BC108. I've never heard about BC508. Here, let's go to the internet and find out. I don't think there's a BC508.
It's there.
I've never had a BC508.
548.
Oh, 54. Even that one I've never had myself. Are you sure it was a 548? Did it look like something like this? Moses, I'm talking to you.
I think we are searching like 548. It's BC 548. That's what we are using, and I think we end the pinout data. BC 548.
Oh, okay. Okay. I'm looking for the manufacturer. It's Motorola. It's a Motorola transistor. $600 milliwatts transistor. So 65 volts we can put. HFE about 90. Okay. So all of them are BC508, so they're silicon. So anyway, when you're designing with a small signal transistor, normally you pick the collector currents to be approximately 1 milliamp when there's no signal. 1 milliamp or 2 milliamps, 1 to 2 milliamps. If you want more gain, you use 2 milliamps. But we can use 1 milliamp. So 1 milliamp will flow over here, 1 milliamp will flow over here when there's no signal. So here you need 2 milliamps. So you go to bias, say that you got 2 milliamps over here. So So depending on the amount of stability you want, if you pick this to say be 1K, you can pick this to be 1K, or you can use 2.2K. But you don't want it very high, because when you use a high drop over there, then the emitters of the differential, the emitters of, let's say, Q1 and Q2 cannot go down so much. The dynamic range will be slightly limited. So if you pick 1 milliamp and use 1K at the emitter of Q3, first of all, you design with a constant current source. So Q3, you want it to be passing 2 milliamps. So the voltage at the base of Q3, if you pick 1K, if you use 1K over here, so it'll be about, so this will be 2 volts. So the drop over here will be 2 volts. Two volts from minus VEE. And therefore the base voltage over here will be about 2.6. About 2.6 or 2.65 volts. I normally use 0.6 volts for silicon, but some of you are told to use 0.7. But you can check in the labs. So then you just have to design for the potential divider. Now this RB, let's call it RB2. And this top one, RB1. Now RB1 and RB2 depends on the input impedance, so the input resistance you want your source to see. Okay, so you have to design it, because this point here is 0 volts, but I like designing from minus VEE if I use that as my reference. So the drop at the base of Q3, so voltage base of Q3 should equal to, what voltage we're using as the supply voltage, plus 10 minus 10, or in the lab, what voltages are using? Somebody just switch on your mic. Are you using 10? I'll use 10 volts. So if you use 10 volts, then you want RB is 2.65 volts, which equals to that, should equal to 10 times RB2 over RB1 plus RB2. So the choice of RB1 and RB2, they're seen in parallel with the supply voltage. So let's call this one Vx, and let's call this source Vy. So the source Vy actually sees 3 resistances in parallel. It sees RB1 in parallel with RB2 in parallel with HIE. Now I don't know, let's see in the circuit if you got a decoupling capacitor. Let's look at your circuit. No, there's no decoupling capacitor at the emitter. There's no decoupling capacitor at the emitter. So the input impedance seen at this point over here will be quite high, which is good. So it means that because the input impedance seen at the input to the transistor Q3 is approximately beta into Re, if you call this resistance here Re. And if beta is around 100, Re is 1K, so 100K. So the input impedance will now be essentially RB1 in parallel with RB2 in parallel with 100K, which will be just RB1 in parallel with RB2. So next you have to pick what is RB1 and RB2. That one can leave to you people to decide. That depends on the source impedance you want. If we pick RB2 to be 10K, then you just substitute in this equation over here. So in this equation over here, this equation, we have 2.65 volts should equal to 10 volts times RB2. If I use 10K over 10K plus RB1 plus RB1. So you can solve for RB1. So this is 10K plus RB1 is equal to 10 volts. Oh, there's not space over there. I'm trying to get another place. My socket is too big. Let me write out the left-hand side here. Top left. So you'll get 10K plus RB1 is equal to 10 volts divided by 2.65 volts times 10. And therefore RB1 should equal to 10 divided by 2.65, 10 divided 2.65, 3.77 times 10K is 37.7K minus 10K. So that will just be that's 27K. And 7.7K is equal to RB1. Now there's no resistance of 27.7K, so which is the nearest resistance that you can get? They manufacture 22K, they manufacture 33K. So you can use, I think the nearest will be 33K. So RB1, you can use 33K. Which you can get in the lab. So it will still work. So next what remains is the resistances, the load resistances, the RLs. Now 1 milliamp is flowing. So you want to drop approximately half of the 10 volts. So you want a drop of approximately 5 volts. and you got 1 milliamp flowing through RL. So 1 milliamps times RL should be approximately equal to 5 volts. So you can use 5.6K. It will work. Or you can use 4.7K. You can also use 4.7K, it will still work. The dynamic range will be decreased a bit with the 4.7K. So lastly, what remains is the RBs. So RBs will also determine the input resistance seen by the voltage Vx. Now, the only criterion that RB should satisfy is that the base current that flows through it should be able to bias, because the current will be flowing, should be able to bias our transistor. Our transistor has got a gain of over 100. I was seeing from the data sheet it's over 100. So it means the minimum requirement of the base current will be 1 milliamp divided by 100. So, and the higher the RBs, the better, because the RBs, the symbol Vx sees RB as one of its loadings, as its input resistance. So the higher the RB, the better. But RB should not be so high that the transistor cannot provide a collector current of 1 milliamp. So how do we design for RB? So let's use this equation over here. Let's consider I small b to be the bias current of the transistors. Times RB. Sorry. First IB times HFE it should be greater than 1 milliamp. And if we take HFE to be 100, it means IB minimum should be 1 milliamp divided by 100. So how to design for RB? Now that one I leave to you, but me, all I can say is that the resistance can be anywhere up to maybe 50K. The resistance can be anywhere up to around 50K. So as a thumb rule, this I'm just giving as a thumb rule, you can use 56K for our RB. The reason I say that is because when you buy this Q3, the voltage at the emitter will tend to go to, because we've dropped about 2 volts at the emitter. So if Q3 is saturated, then the emitter voltage from the 2 will be about maybe 2.2 volts. So the drop from the base of Q1 up to 2.2 volts from minus 10. So 2.2 volts means this voltage will be approximately 8. Sorry, my pen has run out of charge and time is going. So when you buy Q3, its emitter voltage is 2 volts, and that transistor Q3 will try to turn on, and the lowest it can go, Q3 turns on, the difference in potential between the collector and emitter of Q3 will be about 2.2 volts for silicon. And therefore, the collector of Q3 will be, say, 2.2 volts from the emitter of Q3, but its absolute potential from minus VEE will be minus 10 volts minus 2, minus 10 volts plus 2. Sorry, minus 10 volts minus 2.2. So if we say it's approximately 8 volts at the collector, sorry, minus 8 volts at the collector of Q3, then the potential difference from the collector of Q3 all the way to the base of Q1. Remember, the other side of the RB at the base of Q1 is ground. So the maximum potential difference between the grounded side of the base of RB of Q1 to its emitter will be about 8 volts, or slightly less than 8, maybe 7.8 volts. And therefore, the current that will try to flow through RB is about 7.8 divided by RB. And that current should at least satisfy 1 milliamp divided by 100. So that is how we design for RB, the RBs, the biasing resistances at the base of Q1 and Q2. And just from a thumb rule, you need about maybe 50K, 56K. You can go all the way. Let me just see. Because the base emitter junction of Q1 just acts as a diode. So let me just, I've got a calculator here. Let me just calculate. If, for example, RB is 56K and the drop is 7.8, so 7.8 divided by 56K. So that will give you a possible base current flowing of 0.12 milliamps. But the minimum requirement is that IB should be 1 milliamp divided by 100 if we take HFE to be equal to 100. Okay, so with 56K, it will be that. Even with 100K, even if I was to use 100K as RB, so I'll get 7.8 divided by 100, which is 0.078 milliamps. And the minimum requirement is 1 milliamp divided by 100, which is 0.001. Okay, so I'll stop the design over there. So you can use 56K over here. You can even go all the way to 100K. Okay, if you want a higher input impedance. Okay, the design requirement is that this RB must be able to supply at least the current that the biasing current that flows through this RB times the bit of the transistor should be at least 1 milliamp at the collector. So I'll stop over there. I'll stop over there for today. Okay, so you can use lower resistances. You can use even a 10K, but the problem if you use 10K, then the loading on the signal Vx will be more. The loading on the signal Vx will be more. Normally with the multipliers, you want the loading of the signal Vx to be approximately equal to the loading of the signal Vy. Now, one last important thing in the lab is that we use oscilloscopes. And with this circuit over here, if you had to take the output voltage through the collector of Q1, and first of all, remember, the oscilloscope, you cannot connect between the collector of Q1 and the collector of Q2. You cannot do that. Let me just draw it over here. My pen is ready. This is, let's assume this is the input of your oscilloscope. And that's why some of you are not getting signals. Let's assume this is the input of the oscilloscope. You got the live signal, and then you got the earth. Connect to the body. So normally you connect a signal between there. So let's assume this channel A. This channel A. And then you have channel B. And the ground, you have a ground which is connected. So this is a channel B input. So let's assume this is the output of your multiplier. This is the output of your multiply. Now, if you connect this one here and this one here, and remember you got a power supply also. This is your power supply. We will have maybe a positive, negative, and some of them, the negative is grounded to the body. I don't know which power supply you're using. So some of them, the negative is grounded to the body and it's grounded to the earth through the plug to the earth terminal. And the oscilloscope also, the body is earthed through the socket to the plug. And this earth goes all this way. So this is your oscilloscope. Then you're going to have problems. I don't have time to explain it, but you're going to have a lot of problems. And then also the way to eliminate this problem is either to put a capacitor on the earth side. And then you can put the scope into AC. But the biggest problem comes, so this is the top, this is the output circuit. Now the bottom part, this bottom part over here, what the signal VY is. You cannot put channel 2, let's assume these are the probes of channel 2. You cannot put channel 2 here, this is channel 2. And then this is the ground of channel 2. Because this ground of channel 2 is going to be connected to one of your channels over here. When you're trying to monitor the output. I don't have a lot of time to explain it very clearly, but what I just want to say, you've got to be very careful, especially when you've got a three-way power supply like this. You always got to remember that the scope is designed like this. Channel A, the middle is live, the body is grounded. Channel B, the body is grounded. So if you're monitoring one signal from minus VEE and you put the body connected over here, this body of channel B is going to be grounding one of the inputs of channel A, because inside the scope, those 2 points are connected. So the way to do away with that, you go to isolate the grounds by using a capacitor in between. You go to isolate the two. Now, lastly, in the design of the capacitor, this just forms a low pass filter. So the minus 3D point is when what? The reactance of the capacitor is equal to the reactance of this RB. So the higher the RB, the lower the capacitance you can use. See, it's just a simple high pass filter. So when the two reactances are equal, then that gives you the minus 3 dB cutting point. because the response would be something like this. So this is frequency, and this is the amplitude of the voltage going to the amplifier. So the minus 3 dB point is when XC is equal to R, or 1 over 2 pi FC is equal to R. So if you know R in terms of ohms, you can design for the cutting point, cutting frequency. For example, if it's a high frequency multiplier, then C can be very tiny. But if you want to multiply at the audio frequency range, then C will have to be large. Okay, I've taken too much time. I think I'll stop over there. Unless there's any questions.
Hello, sir.
Huh?
I was asking, please, if you could upload the sketch notes and the other notes in Google Classroom, please.
If I can upload what?
The sketch notes.
The sketch notes, but I've given you everything inside my type notes. I've given you people everything in my type notes. I've taken all the trouble to type. The sketches are only used to explain maybe points which are not very clear. Okay. And the other way in the lab that you can get the output of this circuit it is difficult with the scopes that we have unless they're isolated. If the scopes are isolated, then this experiment is simple. And that's why, once again, we need the signal going to the bottom transistor here to be with respect to the ground, then life is easy. If the signal, for example, where's my notes? You see in this circuit over here, in this practical circuit, in this circuit over here, to do it in the lab, this one is very, very simple. Okay, so you can bias this one and put, for example, in this one, after you bias it, like it was that same one in the lab. So you repeat the same over here. And then the outputs, these two outputs, come to your difference amplifier, and the output V naught is respect to the other. So for this circuit over here, all the signals have got a common reference. So if you got a scope, input, the grounds are all common. So this probe can go here. This probe can go anywhere. You can, this other channel can go anywhere. You can either put it at point A, you can put it at point B. You can connect this to either point A, you can connect to either point B. There won't be any problem at all. Okay, I think I'll stop over there for today. And you people should also try the problems. I've done all that I can do by typing for you all the notes. Okay, so which other lab did you have a problem with?